Hello, everybody, and welcome to the Varsity Tutors StarCourse series, where we are so amped to have our friends at the Liberty Science Center in New Jersey joining us for another electrifying lesson. Today, we're going to explore the relationship between electricity and magnets, better known as the field of electromagnetism. Now, before I hand over the controls to Rosa and Alejandro, I want to make sure everyone is ready to collaborate and learn, because alongside a whole lot of learning, we're going to be getting to do a little bit of coding today. And Rose is going to have the details for the free platform vr.vex.com that we'll be using. So be sure to follow along with her instructions if you'd like to code along with today's class. And if you'd prefer to watch and learn from Rosa, that's perfectly okay too. You can always check back in on this recording if you'd like to pause and learn at your own pace. Now, as we move through the lesson, you'll also probably have some questions, and Rosa and Alejandro will have some questions for you as well. So feel free to use the chat panel on the right-hand side of your screen to ask and answer questions throughout the lesson. If we don't get to those questions right away, we're going to have about 10 minutes at the very end of the lesson specifically set aside for Q&A. You'll also want to make sure that you have your cameras close by, because I'll also have the opportunity to lean into the screen and pose for a selfie. And if you tag us at Varsity Tutors and the Liberty Science Center on Instagram, you'll be entered to win 4 free tickets to the Science Center, as well as enrollment for one to Varsity Tutors Coding Camp. Now, I'm going to talk a little more about the details of that prize and how to enter toward the end of the class. But for now, I'm going to go ahead and hand things off to your instructor for today, Rosa.
Hi, everyone. It's so wonderful to meet you all today. And along with me, I have my colleague, Alejandro, who is over at Liberty Science Center.
Hello, everyone.
We are going to get started. I'm going to be able to share my screen so that you can see a lot of not only the platform, but you can also follow some of the instructions. And we're going to do a lot of questions, and I'm going to gauge your answers through the chat. So I'm going to start off by showing the screen. So as Haley said, we are going to be learning about electricity and magnetism and combine those together to make it an electromagnet. And so in order for us to understand it, we're going to start with an activity. The first activity is going to ask you to go ahead and look at the items that are on your screen. So right now we have an aluminum foil ball, a paper clip, a quarter, a brass fastener, one of these little sandwich zip ties, or one of the little sandwich ties, a pipe cleaner, and a penny. Now, what we want to find out is which of these items we think is attracted to a magnet, or in other words, can be magnetized by the magnet. So go ahead and enter it in the chat, list by list. And you can say Y for yes, that it is going to be attracted by a magnet, or and for no, that it's not going to be attracted by a magnet. So go ahead and take a moment for that. We love listening and seeing all your replies to our activities. So definitely share your thoughts with us. So yes or no. What do you think about the aluminum ball? Aluminum foil ball? What do you think about the paper clip? How will the quarter react? Will the brass fastener be attracted by a magnet? Will the sandwich tie be attracted by a magnet? How about the pipe cleaner? And what about this little penny? Excellent, excellent. So keep adding. I know you might not be finished just yet, but keep adding those comments in. I see them coming in. They look wonderful. These are predictions. So let's see what happens. So I am going to bring a magnet over. We're going to play this little video. I'm going to bring a magnet over, and I'm going to hover it over each item. So there's my magnet. It's a small magnet. And I'm touching the quarter. no reaction. In fact, I didn't mean to touch the pipe cleaner, but it got attracted. Penny did not get attracted by the magnet. The brass fastener did, aluminum foil did not, and the paper clip did. So our results are the following. We have the aluminum ball, the coin, well, the aluminum ball, the two coins that are not attracted by a magnet, and then we have the brass fastener, the paper clip, and the pipe cleaner that are attracted by the magnet. So here's another question for you. What do the things that are attracted by the magnet made up of? Yes, so I'm seeing a lot of comments that they're made up of metal. Yeah. And so what can we say about the things that are made up of metal? What can we say about the things that are made up of metal? Oh, I love the comments coming in. Yeah. Excellent. Interesting. I love the thoughts that are coming in. So the end result that we have is that not all metals are made of, not all metals are attracted to a magnet, but magnetic materials are usually made up of metal. So that's a very important thing. So what we saw here is that a lot of it may be made up of metals, but not all metals will behave in the same way when a magnet is brought towards it. So some metals can be attracted to a magnet and some metals are not. So you might be thinking, what does this have to do with electricity, magnetism, and electromagnet? Well, for that, we're going to go to Mr. Alejandro over at Liberty Science Center, who has a little demonstration for you, because both electricity and magnetism result from the same phenomenon. I'm going to send it over to you, Mr. Alejandro.
All right, thank you, Ms. Rosa. So, as Ms. Rosa mentioned, I do have a small demonstration to show you all. So let's go check it out. Now, what I have here is a clear box, all right? But it's not just any box. And I'm going to try my best not to show too much glare because it's pretty shiny. There we go. But you notice that there's some things at the bottom of our box here. I do have some liquid in there, but I have some black flakes there at the bottom. So if I were to shake it up like a snow globe, you notice that now it's a little bit more black in color. So what's floating in there is actually a collection of iron filings. So this is an example of what we call a ferrofluid. So ferrofluid, which is F-E-R-R-O, fluid. So this was made, well, I wouldn't say this type of ferrofluid, but ferrofluid as a concept came to be in the 1960s when space travel was pretty big in its beginning. So they wanted to use ferrofluid as a form of liquid rocket fuel that they can use on their capsules while it's weightless in space. So they wanted to charge up an electrical charge, attract that fluid to the fuel pump, so that way they can use that fuel. So, needless to say, they didn't use it that much for that, but you know, we now have ferrofluid in its existence. So, what I'm going to show you here is I have a magnet. All right, so if I were to place that magnet in that capsule there, something should happen. So I'm just kind of shaking it off screen there. And I'm going to place it right inside. And maybe you should see something happen. We're going to let it settle for a little bit. But what this is supposed to show us, as Ms. Rosa kind of mentioned, is the whole idea behind electricity and magnetism. So, as we define magnetism, all right, it's a physical phenomenon. All right, so it's produced by a moving electric charge. You can sort of see it right there at the above. What's going on there? I have my magnet right in the middle there. You should sort of see those filings kind of collecting at certain points along our box here. So what you get to see here is that this magnet has what we call an electromagnetic field. All right. This one, in terms of the magnet, particularly, it's more a magnetic field than electro. But you have all these different electrons, which are very, very small subatomic particles. And Ms. Rosa might mention a little bit more about that. But if you think of electrons, think of electricity. Electricity powers things up. So what's going on here is that those electrons are actually kind of hanging about our little magnet here. So if I were to leave my magnet there on its own, all right, we have those electrons being pulled or pushed away depending on what end of the magnet you're looking at. So what this ferrofluid does, it gives you a nice visual representation of that field. And you can see right at the bottom there how all those little filings are kind of collecting towards the north pole of our there we go. There's a nice little demonstration there of our magnet. So you see a mixture of pulling in towards the magnet and then a little bit of pushing away to see that a lot of it starts collecting on this end right here. All right, so that's pretty cool. But let's talk a little bit more about the electromagnetic part. All right, because what you can see is that some things are naturally magnetic. All right, so you'll find a lot of metal out in nature that does have that magnetic pull, but we can induce an electromagnetic field. And by doing so, we need to have an interesting looking circuit. All right, so what I have here is a steel drill bit. All right, even though it may look like copper, but it's actually just coated. So there's the actual color right there. It's pure steel. What I have it wrapped around is a copper wire. And I kind of have the tape so it just can stay there. And so the whole idea is that this wire acts as a conduit for electrons to move about. All right, and we have some alligator clips that kind of extends to it. And I have a power source. All right, so here is a battery. So when we talk about circuits, we're providing a pathway for those electrons to move about. And using the energy from those electrons, we're able to power up our devices. Obviously, batteries come in different sizes, so you wouldn't see a 9-volt battery hooked up to our cell phone, for example, or our tablets, right? So if I were to hook up and complete this circuit, so now I have a pathway for that electricity to move about. And the whole idea here is that this steel bit is magnetic. And so what's happening here is that the battery has those electrons charged up. And because we're relying on the magnetic properties of our steel bit, it's attracting those electrons to travel through the little pathway. And it's going to be traveling through that little copper wire. And at some point, it's going to be repelled or pushed away and kind of go back to the battery. And it's just a never-ending loop. So if I were to put it in here, and I will say that it's not very strong. It's a very, very weak field, but it still exists. If I were to put my drill bit right in here, if I were to place some of that fluid, you can see that right there, right where my finger is, you see a little bit of that iron filings still getting close to the cylinder where my drill bit is. And if I were to take away that circuit, you'll see that a lot of that magnetism kind of goes away. So our drill bit is still a little bit charged, but eventually, if I were to leave it in there long enough, you'll see that those iron filings will actually kind of settle back down to the ground. So there you have it. A little bit on electricity, on magnetism. So you can see that there is a nice relationship there, that they kind of go hand in hand. So you can either have something very magnetic in its natural state, or you can induce it just like we did with a small circuit right here. All right, back to you, Miss Rosa.
Awesome, excellent job. And I hope the students saw the connection between electricity and magnetism. But just in case, let's just go over some takeaways. So electricity and magnetism are two related phenomena that produce an electromagnetic field or electromagnetic force that can push or pull things towards it or away from it. So once those electrons are moving, then it generates a magnetic field. So Mr. Alejandro was able to connect a battery, wrap a wire around that steel bit, and generate a magnetic field so that it could attract those iron filings to it. It didn't last forever because it's going to be only an electromagnetic item, which loses its property of magnetism over time and very quickly. So it's not a permanent magnet. It's not going to constantly be attracting or pushing items around. So there you go. That is the relationship between electricity and a magnet. So have fun safely with both. But today, we're going to continue this journey of coding a robot to do some cleaning up for us in this make-believe situation. So what we want to do is I'm going to demonstrate for you how to toggle between, how you can toggle between the classroom page that you have versus your Vex page. So in order to open your Vex window, please open a new browser, and you want to type the vr.vex.com in that new browser. So take a moment to do that. When you've taken that moment to do that, come back to your classroom page so that you can follow along with me and I can help you code this little robot. And I also want to introduce the robot to you. So if you're with me back in the classroom page, then what I want to show you is this little Vex robot. It actually has an electromagnet at the front of the robot, and it also has a couple of actually sensors. It has a lot of different devices that can help us code an assortment of different tasks. But for today, our focus is the electromagnet. So that's where we're going to stay with. And what your page should look like when you finally get to the Vex, so we're going to transition, we're going to toggle. If you're on a tablet, you want to just press the Vex window. If you're on a Mac, you want Command Tab. Or if you're on a PC, it's Alt Tab to switch between one item, one window versus the classroom page. So now I'm showing you the Vex page. So the Vex page, so you should be with me right now in the classroom page so that you know what it looks like, and I can also walk you through it first before we actually get into coding and you get too much into it on your own. So you should all be with me in the classroom page. So right now, I would just want to walk you through what you will see in a moment. So you have all your code on one side, and the code is color coded. We're using block coding for today's program because it's nice and gets us to think about our process a little bit easier than different types of coding languages. So we're using block coding for today. And you also have, you will also have like a green little box that says tutorial you'll want to close out of that page. Don't leave me just yet to do this. Let me just demonstrate it first. So you want to close out of that page. And the next thing that you want to set up is you want to have your playground open. So you will go over to the top, the darker blue, you'll find the word playground, and you'll want to open it to disk mover. There's actually a drop-down menu that'll allow you to choose disk mover. So why don't you go ahead and go to the Vex page and try to do that. While you're doing that, I'm just going to repeat those directions out loud. So when you are on your Vex page, you'll see all the block coding, and they're color coded so that it's easier for us to use them and to navigate through it. You want to find that little green tutorial box, and you'll want to close it by pressing on the X. The next thing you want to do, you actually want to go up to the top dark blue and navigate over to the right side where you see the word playground. You want to click on that word playground so that it opens up a window, and the window might look like a grid. You want to find where it says grid map and click on that grid map word, and it'll bring down a drop-down menu so that you can select the word disk mover. When you select disk mover, you'll now see you'll actually see 3 different colors, 9 total disks on your window. If you have it set up the way that I've described it, come back to your classroom page to follow along with me first, and then you can try it on your own. All right. All right. So hopefully you're on your classroom page. That'll be great. So let's work on something together. We're going to do this together, and then once you see me add the blocks to the page, you can try it on your own. So in order to, here's our little Vex robot. Our little Vex robot is actually sitting in the first blue box. Now this square is the space that we actually have to move out of and tell our robot to move and grab that little disc. Now, today's program is about electromagnets. So this disc is actually made out of a material that is attracted to a magnet. Our robot is going to, just like Mr. Alejandro showed you, our robot is going to turn on its electromagnet so that it can attract the disc and move it. So in order to move our robot, we actually have a couple of choices. We have our blue blocks, or our dark blue boxes that say drive forward, and drive forward for a certain distance, drive right. So just to experiment, I'm going to click and hold and drag that out to our event starter block. Our yellow block is called an event starter because it's going to run the code that's attached to it. The code blocks that we add fit like a puzzle piece. So go ahead over to the Vex window and add your drive forward to your event starter block where it says when started, and get that part set up first. Then come back to me to look at the next step. So you should all be on your Vex window. You'll grab your drive forward. You'll click and hold and move it to the yellow block, which is an event block. And we will then connect it. Okay. So remember, everyone, while you're on the Vex page, to get to the disk mover playground, make sure you run your finger or your mouse along the dark blue that says playground. You click on the playground, And the default map is a grid map. In order to find grid map, make sure that you click on it to go to disk mover. Okay, so everyone should have their drive forward block connected to your when started block or your event starter. Okay, so come back to your classroom page and let's make some predictions. What do you think will happen when we press the play button on our disk mover window, which remember you can find in the playgrounds right up here. So now that you're in your classroom page, this is where you find this window right here. So what do you think will happen when we press our play button? Maybe some of you already tried it. So in your playground window for disk mover, there's a black triangle that looks like a play button. You want to press it. So when you press it, it's going to allow the little rover to move forward. Unfortunately, it doesn't stop at our blue disk. So go ahead and you try that on your Vex window. So go ahead and press play on your Vex window. And you'll see that rover take off, which is great, but we wanted to pick up those disks with its electromagnet. Okay, so let's come back to the classroom page to see the next part, because we know that's not exactly what we wanted to have happen. So we realized a few things. We actually have to be pretty specific with our code because our robot is only going to do what it's been told to do. If I were to tell a toddler to run, the toddler may run fast, the toddler may run slow, the toddler may run and never stop. That would be a horrible, horrible idea. So we actually want to be very specific with our program. So come back to the classroom page and I'll show you the next step of how to make this more specific. Okay, so now that you're back at your classroom page, you're seeing this live. I'm going to actually place my little mouse over the drive forward and click and hold to remove it. And when I do that, I can put it back into the code and that'll kind of throw it away. What I want now is actually the next block, which is called drive forward. Don't leave me just yet to do this on your own. Stay with me for a moment because I need to ask you a question. So my drive forward has an amount. It has 200 millimeters. That's the distance. So we're getting very specific here. So I don't know how far my rover is from this point to get to the end of that little square. So everybody can see my arrow moving on the little square. I just want to move my rover from the corner, from one corner of that little square to the top corner of that same square right here. I don't know how much of a distance that is. So I need to work in small increments. I can't go with big numbers because it might give me that crazy drive forward. So enter into the chat the distance you think I should try in order to move this to this area where my mouse is right now. So go ahead and enter that into the chat. And all I need is numbers, small numbers. Okay. Yeah, because all I want it to do is I want to move my rover from one corner to the next corner. And that is moving that whole length for that little square. I'm seeing some great answers coming in. Thank you, my young programmers. Okay, so I'm going to try 100. Now, how I did that was I clicked I clicked into the little white box. I just pressed and clicked, and now I can type. So I'm going to put in 100, like someone said. And I'm going to press play. Don't leave me just yet. Watch first. Oh, that's only halfway. That's only halfway. So I'm going to redo, and I'm going to keep it at 200. Press play. Oh, it got me to the end of that box. That's exactly what I needed to find out. So it turns out that from one corner to the next corner to the next corner to the next corner in the little squares, it's increments of 200. So we need to figure out how far of a distance, how many millimeters will it take to get to this first blue disk. So let's count by 200s. 200, 400, 600, 800. So let's type in here 800, and now I'm going to press play, but you go ahead to your Vex windows and do just what we did. Grab a drive forward for 800, for 200 millimeters, and let's change that to 800. Go ahead and try it. So again, I'll repeat it a couple of times. So what you need to do is you need to take away the old drive forward that did not have the distance. To do that, you hold the old drive forward that was there, click and hold, and then move it to where all the block codes are. And then let go, and it'll throw it out, throw it away. Now, to grab the new code, make sure you grab a drive forward for 200 millimeters. Click and hold that and attach it to the when started block. If you still have a drive forward without any distance, you want to remove that. We don't need that actually. But what you do want is the drive forward for 800 millimeters. And so in order to change the 200 that's there, remember you have to click into that white little spacing, then type in 800. And when you have it, press play. So you're going to make sure that you have the when started connected to the drive forward for 800 millimeters. And you should see your rover over that first blue disk when you press play. Now, if you're successful, come back with me because that's only the start. So come back to the classroom page, and we'll do the next part together. Because I did mention that this is an electromagnet. So we have to turn it on in order for it to start behaving and creating that magnetic field so that we can attract the metal disc and start cleaning up our space. Okay. So now that you're in the classroom page, this is what we're going to do. So in order to reset, whenever we do code, we need to test every line just to make sure that we're doing it appropriately, because you don't want to code 10 lines and then try to figure out what went wrong. So just to give you a little bit more information about this space, you all know the play button, and this is the restart button. So this gets us all started. Don't leave me just yet, stay with me. And then you'll be able to do the codes that we need. So we know that this drive forward for 800 millimeter works. What we need to do is turn on the magnet. So we need to find the magnet code. So we go to our code, a colorful code, and we see the word magnet. We're going to click on it. We only have one option. But here's the interesting part. I'm going to bring it onto my coding page. We energize magnet. I can click on the drop down, the little drop down menu here, and we only see one choice, our magnet. to boost, which means to turn on, or to drop. So in this case, we have choices. We have a lot of flexibility with this little block. So in order to pick up the electromagnet, just like Mr. Alejandro did, he needed to connect it to the battery to make a circuit. So we need to have our circuit turn on. So we're going to make sure that it's on boost. We're going to connect it to that block that we already have. So now we'll have our when started block, our drive forward for 800, and our energized magnet to boost. Okay, so what we're going to do is we want to come back to the initial box here, our blue box. So let's do one more thing. We're going to grab our drive forward for 200 millimeters, a new one, and we're going to actually change the forward to reverse. And we know how far back it would be to get to the to the blue box, because it was 800 to get there, so it'll take us 800 to get back. So let's enter that and go ahead and do this code and press play. So go over to your Vex window and I'll walk you through this part of it. So now that you're in your Vex window, I want you to drive forward for 800. That should be already there. You want to find your energized magnet to boost. You want to grab that block of code and you want to connect it to that drive forward for 800. Then you want a third block that the next block that you want will be your block number 3 for your code. You want another drive forward for 200 millimeters from our choices, and you want to attach it right below the energized magnet. But this time, what you wanted to say is drive reverse for 800 millimeters. So I'll tell you the order again. When started, drive forward for 800 millimeters. Energized magnet to boost. Drive reverse for 800 millimeters. And you should press play to see the results. So at this point, you should have your little magnet attached to your rover, and that is our successful part. So I'll tell you one other thing. So this is kind of a pattern that we're going to be seeing. We're going to be seeing this pattern of go for a distance, turn on the magnet, drive back that distance, and in order to drop the magnet, you actually have to tell the robot to let it go or to turn it off. So that's the last piece of code that we're going to add. So come back to the classroom page and I'll show you what it should look like. So if you're with me in the classroom page, I'll show you a quick way to do this and then we'll transition out. Okay, so you have your drive forward, magnetize on, drive reverse, magnetize off. So that'll actually get the magnet, bring it back and drop, or sorry, get the disc, bring it back and drop it. So now you need to figure out, how am I going to collect the next 2 discs using this same line of code? And on that note, we'll throw it back to Haley.
All right, wonderful. Thank you so much, Rosa. And I think we've got plenty that students can continue to explore and continue to learn about along the way. Now, it is about that time. We're going to turn things over to Alejandro for our selfie. And before we do, he's got a pretty super representation of electromagnetism to share with you guys. As a quick reminder, if you lean into the screen, you pose for that selfie and you post those selfies on Instagram and you tag us at Varsity Tutors, as well as the Liberty Science Center, you'll be entered to win those 4 tickets to the Science Center, as well as a coding camp enrollment. And in that coding camp, you'll take a week to learn with fellow students more about the foundations of coding and development through game design. You'll have the chance to work on collaborative activities activities with fellow coders, to complete after camp challenges, and even to receive some specialized content from camp celebrity guest stars. So with that, I'm going to hand things over to Alejandro so he can show you the pretty cool example of electromagnetism that we're going to be taking a look at.
Absolutely. Thank you, Haley. So I just want to preface this that I actually have a friend from work, all right, that decided that it'd be cool to let us borrow it and show you all. So if that wasn't a good reference, that friend from work, maybe this will kind of surprise you. So what I have here in my possession is Mjolnir. I think I pronounced that correctly. I think he would be pretty proud of that pronunciation. But here is Thors Hammer. So what we're going to do is we're going to take a quick selfie, and I'll talk a little bit more about the hammer and how it works, and then we'll take some questions. So here we go. So be on the ready. On the count of 3, I will count down, and we'll scream out cheese, and you can have your selfie. All right, here we go. 1, 2, 3, cheese. All right, so I'm going to keep it on the camera there for a little bit. I'll speak off camera, but what we have here is Thors Hammer. So we actually had a really talented group of exhibit maintenance workers and exhibit designers that we all came together and made this beautiful piece of art that you see here. So as Haley kind of prefaced, this is an excellent example of electromagnetism. All right, so as you can see here on our base, you notice that we have a little symbol there, a nice sigil, and it lights up. What you may not hear at the moment, but I can actually hear it as I'm standing next to it, is that there is a brief hum going on. All right, so what we like to do is we like to do a little bit of a prank with our guests. What we tend to do is we have myself or Miss Rosa or anyone that's part of our team that works with the hammer. We just lift it up, and as we all know, whosoever holds the mighty hammer, if they may be worthy, shall possess the power of Thor. So we scream that out loud and we lift it up, and it's a 35-pound piece of equipment. So if we were to lay it down regularly, you might hear the hum now. So if I stay a little bit quiet. And so what's going on here is that we have a giant electromagnet right in the base. And when a guest tries to lift it up, it is practically impossible. So what I have here is, oh no, right there. I have a nice little receiver. And when I touch the buttons on the receiver, I turn off the magnet and I can easily lift it. So every time we lay it down, all we have to do is just turn it back on, have a guest try and lift it up and see if they're worthy, and they'll find out that they can't because of that electromagnet. So what turns out to be a 35 piece of equipment with that electromagnet on, it weighs about 500 pounds or more. So you would have to like counteract that weight to lift it off from the base, but we haven't had anyone do that so far. So there you have it. We got Thors Hammer. It's a pretty cool piece to just kind of walk around the museum with too. It's a nice photo opportunity. All right, so any questions?
Awesome. That is so, so cool. And I'll probably, take a step back from the 500-pound workout lift. I think the 35 pounds is plenty enough. We had lots of really wonderful questions. We had students who were wondering what other sorts of things they can test magnetism with and electromagnetism, and in particular, whether any of the experiments that you went through today are safe versus not so safe for them to do at home.
You want to answer that, Ms. Rosa?
Absolutely. Thanks, Mr. Alejandro. So all of the experiments that you saw here are very safe to do at home. If ever you find that there's a really strong magnet, what you want to do is not put it near credit cards, telephone, things that are important to you, because it might interfere with it or even, null the programming behind it. So be careful on how you play with magnets, but it's certainly, you can make an electromagnet using batteries, wires, a little bit of tape, and a material that can allow itself to be magnetized. So something with steel would be a good idea.
Very cool. And we also had a very interesting question around the science. So how is it that you can determine how heavy that electromagnetized hammer truly is? How do we figure that out?
Good question. So that was actually tested out by our exhibit workers. So I forget exactly what device they use, but they know for a fact that the electromagnet that we have in the base is actually part of a replacement part that we have for a big demonstration that we have in one of our exhibits that relies on these electromagnets to keep something very sealed in order to run this demonstration. So they had some extras lying around, and I think based on the manufacturer's details, it kind of tells you the amount of force that can pull in terms of activating the magnet. Now, I don't know if you were able to see, I have a long cord right here in the back. So just like how Ms. Rosa mentioned, you know, as long as there's electricity going, you have that magnet going on. But as far as I know, they had some sort of device to kind of determine once you place the Thors hammer right onto the base.
Wow, very, very cool. Now, we had some students who I'm guessing know a little bit about magnets or have some experience working with them before, who were wondering, when you did the experiment where you put the magnet in to see how those shavings would interact,
Yes.
Does it matter which direction you put the magnet in?
Good question. So it really doesn't matter. So you can actually place the North Pole and the South Pole, you know, at any point, and what you'll see is that if I were to mix it up real quick, if I place the South Pole end at the bottom, you'll see that they'll always collect either in the South Pole or in the North Pole. And so it's a little bit turbid because, you know, I kind of shook it up a bit. You can see how it's all collecting at the top, and you see that black mass at the bottom. So if I were to take out the magnet, and if I put North Pole in first, then what you should see is that you'll have the same effect. Obviously, depending on how you kind of rest the cube on whatever side, you'll see more filings kind of collect there. But you'll always see that collection of filings up at the top and filings at the bottom. You can actually see the little lines on the side there. That kind of visualizes the magnetic field on each side. And I just got a nice visualization there. Look at that. Mm-hmm. All right.
Very
good question.
Cool. Awesome. Now I know we're getting close on time, but we had some students who were really excited with the opportunity to get some foundational knowledge around the way coding works without necessarily needing to know a coding language. So are there any other either resources or steps that you'd recommend for students to learn a little more around the foundations of coding?
So one of the things I like to do is play around and test things out. So always start off, whether you're going to continue with Vex or not, but if you're starting with a block coding program, you want to attach one at a time, each block, and test it out so that you understand what that block does. Because understanding each block and how it performs is going to build your knowledge base, and that will be resulting in a really cool code that you do line by line, test by test, with a outcome at the end.
Absolutely. Yeah. We wouldn't, I know, I can think back to the days of schooling where when you get to the end of a math problem and you did something wrong and you got to walk all the way through all of those steps. We want to make sure we're avoiding that here and that we're learning step by step along the way. That is awesome. And as a quick reminder to everyone, if you wanted to continue to build, if you wanted to continue to pick up each of those discs, you have the ability to move forward, and you could go back and check out this class recording if you'd like to hear Rosa walk you through things step by step along the way. Now, before we wrap things up for today's lesson, Alejandro, Rosa, do you have any other final thoughts that you'd like to leave the class with?
I always like to say, have fun and be curious. Alejandro, what do you say?
Same exact thing. I was going to say, be curious and always tinker.
Absolutely. Well, thank you so much again for another wonderful class. Thank you to Rosa, to Alejandro, to the entire team at the Liberty Science Center. We hope to see everybody back in another StarCourse sometime soon. And we thank you for all of your questions and comments and participation. In the meantime, don't forget to post those selfies and tag us at Varsity Tutors and the Liberty Science Center to win. Thanks, everybody.